Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So today we are doing another video here. Today's video is on hydrogen bonding worksheet number 2. This is the second video, the second worksheet. So make sure that you watch the first video, hydrogen bonding worksheet number 1 first before you start this one. All right, here we go. Part 1, the water molecule. Number 1, draw the Lewis dot structure of water. And make sure again that you watch the hydrogen bonding worksheet number 1. I've gone over detail on how to draw that. And I'm just going to slap this down here. There are 8 electrons around hydrogen, 4 pairs, bonding pairs of electrons first, lone pairs on the outside atoms. You cannot do that with hydrogen, but you can put lone pairs on the central atom like thus. Perfect. All right, a couple other extra things here that we do need to add to this. That is, oxygen is more electronegative than hydrogen. Therefore, oxygen has a partial negative charge to it. This is a lowercase delta, the Greek letter delta. And then this end of the molecule where the hydrogens are, they're more electropositive. So that's going to have a positive end. Water is asymmetric, like I discussed in the hydrogen bonding worksheet number 1, and therefore you can draw a molecular dipole. That molecular dipole coincides with the electronegative end. That's why there's a delta negative right over here, where there's a very electronegative element, that's oxygen, and the electropositive end of where the hydrogens are. That's where that delta positive end is. You should see that the tip of the arrow of the molecular dipole, this is a molecular dipole, this arrow, the tip of the arrow is going toward the negative end. So if I were to knock an arrow, if I were Robin Hood and shoot an arrow at you and it sticks in you, that's negative for you, but it's positive for me because I can see the feathers of the arrow. That's how it works. When a molecule has polar covalent or polar bonds and it is asymmetric, you can draw a molecular dipole. That molecular dipole means that that molecule is polar. And I've already discussed this before on hydrogen bonding worksheet number 1, but it is very similar to that of a bar magnet. Okay, there's one end that's positive and there's one end that's negative. This is the negative end of the molecule of water, and this is the positive end of the molecule of water. So it's just like a magnet. So that means that the water molecules will align themselves up just like bar magnets and electrostatically attract to one another just like these bar magnets are. Okay, fantastic. All right, let's go on to part number 2. So we're going to scroll this on up here and part number 2. All right. Part number 2 is as follows. The water molecule and methanol. Draw Lewis structures of water and methanol. Methanol is CH3OH and the hydrogen bonding between these two molecules. All right, so methanol I have written as CH3OH. The OL on methanol corresponds to this OH group. If it has an OL ending, it's an alcohol. This is the simplest alcohol there is. This is otherwise known as wood alcohol. Okay. And the next alcohol would be ethanol. That is the stuff that older than 21 in the United States can drink legally, not necessarily good for you. And then there is propanol, like isopropanol, that would be with 3 carbons. So methanol is with 1 carbon, ethanol is with 2 carbons, at the appropriate number of hydrogens and an OH group. Then propanol is with 3 carbons, the appropriate number of hydrogens and an OH group. It's very important that that OL means it's an alcohol. I'm assuming that you are familiar with isopropanol. That should be in your bathroom, and it has a particular smell to it. and you use it for at the dentist office, or maybe not at the dentist office, but certainly at the regular uh, medical office, they use isopropanol to clean your skin before they jab you with a needle. All right, here we go. So what we need to do is draw the Lewis dot structure for methanol. So the least electronegative element is going to be the carbon. And then surrounding it will be the hydrogens. There are three of them. That's 1, 2, 3. In the following 3, 6, and 9 o'clock positions. Then there's an OH group. So you're going to find out that you're going to be able to place this O right there. And if you were to count up the number of electrons, there's actually 7 pairs of electrons for methanol. That's very important that you can do that. Perfect. So you'll find out that we're going to try to place these 7 pairs of electrons, and we still have a hydrogen left to place. And if you've been following all my other Lewis dot structures, then you should also understand that once we have an octet, that's 2, 4, 6, 8, we can no longer place any more elements or electrons around that central carbon. Consequently, we're going to have to place that hydrogen right on that oxygen. That will give me 2, 4, 6, 8. That's 1, 2, 3, 4, 5 pairs I'm using. Then I have 2 more pairs of my 7 pairs remaining, and that's going to go on this oxygen because that oxygen is lacking an octet, and it most certainly needs an octet. You should be able to circle each element. That's this carbon has 2, 4, 6, 8 electrons around it. This oxygen has 2, 4, 6, 8 electrons around it. And each of the hydrogen follows the duet rule, which has 2 electrons around it. This is the Lewis dot structure for methanol. That's perfect right there. Now what we're going to do is we're going to do some hydrogen bonding with some water molecules. So what I'm going to do is draw a water molecule that is similar to the previous water molecule that I have right here up at the top. So what we're going to do is we're going to have a hydrogen, that oxygen, and that hydrogen. And it follows that same pattern of 2 single bonds and 2 sets of lone pairs of electrons. Now, what we're going to do is we're going to draw some hydrogen bonds, just like we did on worksheet number 1, except that this is with methanol and water and not water and water. All right, so what we've got here is a polar covalently bound hydrogen will hydrogen bond. That's a special case of a dipole-dipole interaction between an electronegative element on another molecule. So right here is going to be a hydrogen bond. Excellent. So what we have right here is a hydrogen bond. All right, I'm going to give another possibility of a hydrogen bond for you. So we're going to draw another water molecule. We're going to draw it in the same orientation as what we had done just previously. So that should be familiar to you. All right, now we have an electronegative element, that's oxygen, polar covalently bound to a hydrogen, will hydrogen bond to an electronegative element, oxygen, on another molecule. This is also a hydrogen bond right there. I'm going to show you another possibility of a hydrogen bond, and that is this oxygen right here, okay? And this polar covalently bound hydrogen on water will hydrogen bond to this oxygen right there, just like that. That looks fantastic and beautiful. Hopefully that works well for you. I'm going to show you a possibility that is not a possibility that many students at times draw these. And so what we're going to do is we're going to draw another water molecule. It's going to look just like the same as the other ones. I'm going to draw this in a different color so that it will show you the distinction. This one is in black. Okay, and then the question is, can you have, here is a electronegative element, that's oxygen, and a hydrogen. And then will it hydrogen bond to this hydrogen? And the answer is no. Okay, and so here's why. As I discussed in the previous worksheet of hydrogen bonding, worksheet number 1, oxygen has a value of electronegativity of 3.5. Hydrogen has a value of 2.1. That difference is 1.4. That's a polar covalent bond. That's a polar covalent bond. Okay. Now, the problem here is this carbon has a value of 2.4 and the hydrogen has a value of 2.1. Okay. Some people think that the value of carbon is 2.5. So either way, we'll just go for that one. And then our value, our difference in electronegativity is 0.4. So that means that this bond right here is a covalent bond and not a polar covalent bond. So anytime you have a carbon covalently bound to hydrogen, it's a covalent bond. It is not a polar covalent bond like that bond in oxygen and hydrogen. Therefore, this bond does not have a charge separation like what we have drawn in this water molecule here. That's why we cannot hydrogen bond with a carbon-hydrogen bond. That's impossible. Don't do that. It will be wrong. You'll be very, very sad. All right. So let's do the next one over here. Let's slide this on up. And here we go. Okay, so this is one of the major common mistakes. Mistake number one is to hydrogen bond with a carbon hydrogen. That's impossible. That doesn't work. Notice that the hydrogen bonding occurs when it's an oxygen hydrogen. That's okay, but not a carbon hydrogen. Okay. All right. Let's scroll this back on up here and we're going to do part number 3. Hey, before we keep on going here, we need to give our sponsors a big, gigantic thank you. And there's one sponsor for today's video, and I want to thank that sponsor. That sponsor is the Crazy Hat Chemist. That's me. I greatly appreciate if you like, subscribe, hit that bell, and tell all your friends. Tell your parrot to like and subscribe as well, and tell your parents, your grandparents, your cousins in other countries, and let them know this is the place where you are able to learn real chemistry for a strong foundation in chemistry. This is not just fluffy stuff. All right. So thank you to our sponsor. Greatly appreciate that. Here we go. Part number 3, the water molecule and ammonia. Number 2, we're going to draw Lewis structures for water and ammonia and the hydrogen bonding between these two molecules. So what we're going to do is we're going to draw ammonia and we're going to draw water. We're going to draw water just like what we have done drawing before. And that's going to be that oxygen, hydrogen, hydrogen, and we're going to have 2 sets of lone pairs of electrons on that oxygen right there. We're going to draw ammonia, and nitrogen has 5 valence electrons. There's 3 total valence electrons with the 3 hydrogens, so that's 8 total. That's 4 pairs, and we're going to have a nitrogen. We're going to have a hydrogen, and another hydrogen right here. That will give me 1, 2, 3, and a lone pair on that nitrogen. This oxygen-hydrogen is a polar covalent bond, just like what we discussed right above. There's a difference in electronegativity of 1.4. That's a polar covalent bond. So this is a polar covalent bond. This polar covalent bonded hydrogen will electrostatically, with a dipole-dipole interaction, be attracted to this nitrogen. That is an electronegative element on another molecule. This is also a hydrogen bond. Beautiful. I'm going to give you another possibility of a hydrogen bond here. I'm going to draw another water molecule. Okay. Another water molecule. I'm going to draw it in its same orientation as what I have drawn before. Not that it needs to be, but it is in this particular case. This nitrogen is very electronegative. It has a value of 3.0. Then we have a 2.1. So this is electronegative as well. Not as electronegative as oxygen, but still it's highly electronegative compared to the vast majority of elements. So this is also a polar covalent bond between the nitrogen and the hydrogen. It will electrostatically, with a dipole-dipole interaction, be attracted to that oxygen on another molecule. That is an electronegative element on another molecule. This is also a hydrogen bond. I think that looks fantastic. You guys are doing a fantastic job. Now, I'm going to show you mistake number 2. Mistake number two is going to be off to the side here. We're going to draw the ammonia molecule, just like what we have drawn before. And there we go. That looks beautiful. And then we're going to draw a water molecule. Now, this water molecule is going to be flipped, but it's very important of how I have drawn it. Okay, this is a polar covalent bond. That is fantastic. And that is a polar covalently bound hydrogen. Will it electrostatically be attracted to this hydrogen? Well, this is a polar covalently bound hydrogen as well. But is this a hydrogen bond? Question mark. And the answer is no. So I'm going to circle this here, and this is mistake number two. The most common mistake is mistake number two. And that is, I want to clearly state this here. I want you to see that there's a hydrogen and a hydrogen. Hydrogen, hydrogen, that is not a hydrogen bond. Absolutely no way, no how, don't do that. Notice the hydrogen bond is between a polar covalently bound hydrogen and an electronegative element on another molecule, not two hydrogens. You don't see two hydrogens being hydrogen bonded. That's not what a hydrogen bond is. So make sure that that is a clear distinction on your part. All right, now what we're going to do is we're going to do the second half of this worksheet here. So we're going to flip this over. We're going to do the other half on the other side. And here we go. Here we go. Let's see here. Part number four. Part number four. Part number four says, within the structure of DNA, there's adenine and thymine. The structures of adenine and thymine are drawn below. Draw the hydrogen bonds between these molecules. Right? So what are we looking for? In order to form a hydrogen bond, we need a polar covalently bound hydrogen. This is a polar covalently bound hydrogen. And we need an electronegative element on another molecule. So we got two molecules here. We've got adenine and thymine. And this polar covalently bound hydrogen and an electronegative element on another molecule will be a hydrogen bond. Again, this is a special case of a dipole-dipole interaction. All right, fantastic. Can you identify another hydrogen bond between that adenine and thymine molecules? Well, I certainly can. So that is a polar covalently bound hydrogen and an electronegative element on another molecule that will hydrogen bond. That is also a hydrogen bond. So the question is, how many hydrogen bonds are there between adenine and thymine? 2 hydrogen bonds. That's very important here. Okay, your biology teacher will be very proud of you if you are able to identify this. This is in that double helice, in the interior portion of that double helix structure of the 5' to 3' and 3' to 5' anti-parallel strands, you will have the adenine and thymine hydrogen bonding. Now, what we're going to do is we're going to do part 5, and you're going to see the other component of those hydrogen bonds within the structure of DNA. All right, so let's scroll this on up here. Here we go. And part 5 says, within the structure of DNA, guanine and cytosine. For the structures of guanine and cytosine are drawn below. Draw the hydrogen bonds between these molecules. Okay, so what do we need? We need a polar covalently bound hydrogen will be electrostatically dipole-dipole interaction attracted to an electronegative element on another molecule. And that will be a hydrogen bond. Beautiful. That is a hydrogen bond. Can we identify another one? Yes, we can. That is a polar covalently bound hydrogen will hydrogen bond to an electronegative element on another molecule. That is also a hydrogen bond. Bingo. Right there. An electronegative element will be attracted via a dipole-dipole interaction with a polar covalently bound hydrogen on another molecule. That's correct. That is another hydrogen bond right there. So how many hydrogen bonds are there in the structure of DNA between guanine and cytosine? 3 hydrogen bonds. Okay. This plays a critical, crucial role in DNA. So I'm going to zoom out just a little bit so that we can see both of these structures using the adenine and thymine and guanine and cytosine. It's really important that we take a look at both of these structures. Let's zoom out as much as we can so that we can get both of these in here. All right, I think we are right on the cusp of it right here. All right, fantastic. I think we got them right here. So you should see that when you have adenine and thymine, okay, when you have adenine and thymine, you have 2 hydrogen bonds. When you have guanine and cytosine, you have 3 hydrogen bonds. This is why the melting point of DNA, which has a larger GC content, is higher than the DNA, which has a larger AT content. Okay, there are 3 hydrogen bonds. That takes more energy to break than 2 hydrogen bonds. Really quite simple there. All right, so what we're going to do is we're going to zoom in here and we are going to do our very, very last problem here today on this worksheet. Okay. Oh, by the way, another key note from our wonderful sponsor, and the sponsor is none other than me, myself, and I, and that is, well, I am the Crazy Hat Chemist. And please, I appreciate you liking, subscribing, and taking a picture of all these videos and sending them to your friends. Okay. All right. Fantastic. So let's move this on over here and let's see what we can do now. We're going to make a list of properties of water based on hydrogen bonding. So there are many. This is a partial list. This is not a complete list, but this is a partial list. Okay. So the solid, and that is ice for water, is less dense than the liquid. And I did try to explain this in the very first video on hydrogen bonding, but if you missed that, I'm going to show you what that means. So you should see here that I have, right now, I have a lot of water molecules. Each one of these is representing water. And so what I'm going to do is I'm going to represent liquid water. So liquid water, in liquid water, there's between 2 and 3 hydrogen bonds. And you should see that liquid water is constantly moving, breaking and forming hydrogen bonds constantly. And I want you to see that as these molecules move back and forth and exchange places and break hydrogen bonds, forming hydrogen bonds, there are no large gaps in between the water molecules. That means that water is relatively dense. However, once water reaches a certain temperature, then what happens? Then there is a maximizing of the number of hydrogen bonds within the water molecules. And that forms this structure right here. So I'm going to show you 2 different ones. There's a central water molecule, and that is this one right here. So where's the central water molecule? This one right here. And how many water molecules can surround at maximum this central water molecule? 4. That's 1, 2, 3, 4. This is what happens when water freezes. And it forms this pattern right here, which is a hexagonal crystalline structure. So that's hexagonal. Hex is for 6. So that's 1, 2, 3, 4, 5, 6. So this hexagonal crystalline structure has an open cage network. So see this right here? That was not available in our liquid water. This is representing liquid water. And this right here is representing solid water. That's ice. There's an open cage structure, and that is an increase in volume for the same number of water molecules. And that is why water in the solid state is less dense than the liquid state. All right. Fantastic. All right, what other awesome, cool properties are there with water due to hydrogen bonds? There's a high surface tension. And with this one right here, this is very important. So I want you to go and try this. So if you have a pool or a friend that has a pool, or you can go to your local gym that has a pool, okay? Wait until nobody's in the pool and it's nice and glassy surface. And then what I want you to do is I want you to do a belly flop, like jump in the pool, belly up, or belly down rather, and slap yourself right on that pool. Boom! You're gonna ask yourself, does it hurt? And the answer is, oh yeah, baby, it hurts. Then you're going to try this experiment another day, another time, because you need some time to recover. And what you're going to do is you're going to wait until everybody is in the pool, jumping, yelling, screaming, splashing, and you're going to jump in the pool, do a belly flop. And will it hurt as much? No, because when everybody's splashing and everything, they have broken up the hydrogen bonds in water, and that's why it doesn't hurt as bad. Okay, this is why you can float a paperclip on water. There's a high surface tension. There's a number of hydrogen bonds, and those are not necessarily broken. Another property based on water and hydrogen bonding is that there is a high melting point. And this also goes with a high boiling point. Now, water has a very low melting point, or rather high melting point, but it also has a high boiling point. And so there is no other structure, no other molecule that has such a high melting and boiling point based on the, because the hydrogen bonds, okay, it's impressive as far as the boiling point and its molar mass. So nothing that has a comparable molar mass of 18 grams per mole has such high melting and boiling points. What else is really cool based on hydrogen bonding? Well, water is a liquid on planet Earth. Now that is impressive, because if it weren't for the fact that water is a liquid on planet Earth, I would not be alive today as I am currently, and neither would you. And we are dependent on it. That is hydrogen bondings and water being a liquid on our planet. Hey, you know what I'm going to do? I'm going to give you two more things here, even though they're not on there. I'm going to give you two more things based on hydrogen bonding. Okay, capillary action. I want you to think about like redwood trees, giant sequoias. They are hundreds of feet tall. How does the water get up that tree? Well, there's very small little tiny tubes in the tree, and they are about as narrow as a water molecule. And between hydrogen bonds and that capillary action, that water will climb up to the very tips of those needles of those trees without any energy consumed by the tree itself, except for splitting the water at the end of those needles. Another one here is the unique crystalline structure. And this would be for ice. So if we were to take a look at an ice molecule, or rather many molecules of water and ice, you will find out that ice has a very unique crystalline structure. And that's very important as well. Due to hydrogen bonding, oh yeah, baby. All right, so this concludes today's video. I want to thank you very much. Like, subscribe, have a great day, and I'll see you next time. Bye for now.